Good morning, everyone. Welcome to today's session. Let me share my screen. Right? It's very simple. Apparently, we have a cart like this, and it has this mass m, right? And we have then a pendulum with the length L, and then basically a bob at the end of this pendulum with mass m. And the question told us to ignore the mass for this guy. So we ignore mass. If you be patient, in few weeks, you will see when we solve similar problem that we cannot ignore the mass L. And in fact, it is important. And you learn how to deal with those sort of problems. But for now, we just ignore the mass. And we push this cart by this force P. We want to find out this angle theta. So this force P, imagine if we don't apply P, what will happen? Well, you know, because we have this mass M, right? mg, obviously it's gonna come down and stay vertically somewhere. Everybody agrees on that, right? Now that I apply this load P, it's gonna push back and stay at an angle alpha if P is large enough. We wanna find out like the relation between this alpha, mg, and P and this big M. Okay, that's basically the problem. All right, so let's see how we can approach this problem. If, since we are still in dynamics of particles, I can treat the whole things as a particle. So then for now, let's ignore these basically. I don't know how can I get rid of these. Okay, so for now, what I will do, I say, okay, can I like consider the whole things as one particle? Yes, because nothing inside this like cloud that I draw is moving, right? Or if I zoom out, if I go out and from distance look at these things, I don't see anything inside. I just see one dot, which this dot has a mass of m plus m. Do you guys agree? And then I see a load P applying to this m plus m. So immediately I can write down that, well, that's good. I know a good relation, F is equal to ma. So simply I can write P is equal to m plus m a. That's one relation that we figured so far. So we keep it for now. It's not going to solve our problem because we are looking after finding this angle alpha. Now I get to inside these things and see what's going on inside, okay? So I'll draw the free body diagram so I can see for this mass M, it has a weight and it is mg. And what else do I have? Well, I know that basically this link apply a load, a tension, and this tension, let's call it T. All right, so we have just one link, and this link either can apply a tension or compression, which obviously from this mechanism, you can see this link is under tension. So this is the force diagram that we have. We can set our X and Y coordinates so we know where we are and what is what. So let's then have like this guy here and this guy there. All right, this is all we have. So this is what we call it a force diagram. Or we call it free body diagram. And I'm sure in your MEC 260, you learn how to draw free body diagrams. If not, or if you forget, I explained yesterday to students, you can go to one of these engineering skill courses. I guess I explained to everybody last Monday as well. That you can check like MEC 260, which I explain how to draw nice, clean, free body diagrams. So, but for dynamics, we need another diagram as well, and that's the acceleration diagram, all right? So always we need another diagram, which we call it acceleration diagram. It means I need to draw these like the same as, let's continue this one so we know where we are. Can I select this guy? Not sure. No. Oh, yeah. Okay. So I draw the same particle that I drew here. It has mass m. And then what sort of acceleration it has? So it doesn't go ups and down, right? It just goes to the right. So it has only one acceleration. Let's draw acceleration with color red. And its acceleration is a. Because this one is part of the whole things. And it doesn't go ups and down, so I don't have anything in this direction. If I manage to draw this diagram correctly, then the rest in dynamics is just math and is nothing else. Simply, we use our Newton law. We write down that sum of the forces in X has to be equal to MAX, and sum of the forces in Y direction has to be equal to MAY. So what do I have in X? Let me write down. In X direction, well, I need to find the components of these forces. Let's do that quickly. So this T, I can break it down to its component. So it's going to have two components. One is this guy, and one is this one. So this one, if this is alpha, it's going to be T sine alpha, and this one is going to be T cosine alpha. All right, so then let's continue. In X direction, I have T sine alpha, nothing else. M, what is acceleration in X? It is A. The only things, if I look at my diagram, in X direction, the only things that I can see, this is X and this is Y. It's just A. And then what do I have in Y direction? I have T cosine alpha, I have mg, and then nothing else, equal to 0. So if I divide equation 1 by 2, what do I get? So I get tangent alpha is equal to, that one goes there, I get rid of m, a over g. And we already found a, right? From this one at the top, we know a is equal to p m over m. So let's put it there. Tangent alpha is equal to P over M plus mg. So we found basically this angle. If this question gives us the value for P, the value for large M, a small m, and then we know gravity, we can find the angle. All right? So very, very simple problem, but important. You need to get a good grasp of what's happening here. And please do not be shy. If you have a question, ask me now so you clear before we go further. As I explained at the beginning, Soon we will see the same problem when this link has a mass, and soon we will see a problem when this alpha is not constant, maybe it's spinning, and maybe the whole thing is part of a big mechanism, which in mechanic and in manufacturing, you will see it a lot. So you'd better to understand like this simple problem before we go to the next step. I'm gonna let you guys to take notes if you want and absorb what's happened, and then we'll move to the next problem, if there is no question. Okay, maybe one question popped up in the chat. So that's a good question. Somebody's asking, well, we will see like the whole things. Let's say, if you look at the whole things, as I said, zoom out from your screen, and let's say you're looking at the whole things from distance, right? If you look at this mechanism from, let's say, 200 meters, you will just see one dot. And this dot has one mass, m plus m. So when we say the whole thing has an acceleration a, which we found it, then because this thing is not spinning or anything, it means any point on these basically things has an acceleration a. It doesn't matter if I look at this point, if I look at this point, if I look at this point, or if I look at this point m. All of them has acceleration a, because all of them are moving in a straight line. All right? So now it's up to me to come here and just analyze a portion of these things. Maybe I cut a portion of that things from the cart, I take it out, and I'm going to study it. So the one information that I have, I know that since this portion of cart that I cut is moving with the whole thing, it has an acceleration a, which for all of them, it's the same. But it's not going to be useful, this portion of the cart for us, right? What we are interested to know is finding out things related to this mass m, which connected to this link. So that's why I just draw the free body diagram for this mass m. Maybe if I wasn't lazy, I should have done a better job and draw the acceleration diagram, like the free body diagram, as like a real free body diagram. I was just lazy and draw it on the system. But in fact, when we say free body diagrams, it means we have to separate it from the rest. Like here, we just cut this mass m, we took it out, and now we draw the free body diagram for it. So what do we have? We have weight mg, and we have the tension from these link T mg. So this is the real free body diagram. Okay. So in your exam, maybe if you do this, I would be happier, better. And now you look at this, like the whole things here. So let me get rid of that. So now you look at these two diagrams. And you guys agree that this mass m is not going to come down or go up. Why? Because the question says, with this force, the pendulum stays in a steady state angle. Okay, so I hope it clears, but if not, I can explain more. So why the pendulum only moves in the horizontal direction? Well, because the question told us, right? The question says that we apply a load, that the load is so big so that, you see here, pendulum stays in a steady state angle. If the same question tells us that, well, find, for example, load P so that this alpha is changing with this rate. That's a different question, which, as I said, in a few weeks, you will see that. But this particular question told us that this load P is large enough that this angle basically stay in a certain angle, maybe 30 degrees. I want all of you to visualize these. Imagine that you build this cart and you build this pendulum with this mass m, okay? So could you visualize that for me? And what is how it is standing? So you will see a cart with the pendulum is just hanging down here, right? So a pendulum is just gonna stay, if I draw, no load P then, right? This is what you will see definitely. So this is what you built. Now I want you to imagine that you apply load P, okay? Very large load P, like probably you've seen in cartoons. If the load P is so large, maybe even this pendulum, it's open up and becomes horizontal. Like the whole thing moves sort of this angle. But for that, load P has to be very, very large, which you can find out how large it can be. For example, if you put alpha to be 90 degree, what is the tangent of 90 degree? It's infinity, right? So it means if you apply a super large force, then you get to, if you want alpha to be 90 degree, then load P has to be infinity. Right? That's why in practice, never we get to that 180 degree. Even if you apply like a super large force, this pendulum comes and stay very, very close to the horizontal line, okay? And stay there. But this question tells us to solve it as a general thing and say, find the relation between P and alpha. Are we good, guys? Or still unclear? Good? I'm going to check chat one more time. Okay, great. Yeah, think about it. And as I said, always try to visualize, like in this course, how things are moving, because it's a dynamic course, right? Even in your static and in MEC 260, try to visualize how the forces are applied. But the good things in 260 is that you don't need this part. Everything here is 0, right? You just need the first part. You need to do the free body diagram, but these 2 star, you don't need it because everything here is 0. Like simply this equation, sigma, like sum of the forces becomes 0. But here, sum of the forces, we are in trouble. On the right side, we have an m and we have an acceleration. Okay, so let's move on and then solve another problem. Okay, this is also a very important problem, and I want you to pay very good attention to it. If you download the previous version, there was a typo which I corrected it, and not a big deal. Like this omega here. This is the omega that we are referring to. So I'll let you guys to read it. And like always, please try to visualize what's happening. It's super simple. And you will get better at it because like you will see as of next week, we will see different mechanism and then you force your brain to visualize more and think more about these things. So what do we have here? And again, this is something that it is used in many factories and in many warehouses and very simple but important engineering questions, which you may go to a job and they ask you, okay, how fast my conveyor should rotate. Okay, like this is the conveyor, this is the belt, and it's attached to a motor, and it's spinning with the speed omega. And we just slide a part at point A, and it comes to point B. Again, let's understand the problem. Let's say the moment that these things is coming down and want to lay down on this basically conveyor. So it has a speed, we know. So it just entered this point and it has a speed. And this speed, let's call it V. So what will happen if this V, okay, that's one thing that we know. Keep it for now. And what else? So we know this conveyor is rotating, and any point on this conveyor has a speed, all right? Like this point has a speed, this point has a speed, any point has a speed. And we know how to calculate this speed. We do, right? So we know that, for example, this belt, as it's moving, any dot on this belt has the same speed as this point. And what is the speed of that point? Well, it's a circular motion. It is r multiplied by omega. All right, so we know the speed of this point, this blue point. We know the speed of these, let's say this box V. What will happen if this V is larger than this, like this red speed is larger than this blue speed? You know what will happen, right? Like the whole thing's come down and then shoot on this conveyor belt, which we don't want it, right? It's gonna slide and shoot and maybe hit the next one because this conveyor is having other parts as well. What will happen if this red speed is slower than this blue speed? Well, try to think about it. If it's slower, it comes down. The belts want to rotate and move, but this thing is super slow. So they are gonna sort of slide on top of each other, and there's gonna be some friction between them. Like the belt wants to move faster, but the box says, sorry, I'm slow, I'm gonna stay a little bit. So there's gonna be a sliding there. So that's why when people design these things, they say these two has to perfectly match. Like V must be perfectly equal to like R omega. So this V has to be equal to R omega. So if you guys agree on this, then we can move on with solving the problem. So as you can see, our first task was here to understand what's going on and find something here to give us a hint for the rest of the problem to solve it. Okay, I'm gonna let you guys think and make sure that you agree with what I just said. Okay, so if we agree with that, now our task is finding out this V, the speed of this box. And I'm going to solve it with two solutions, the difficult solution and the easy solution. But both are important to know because it depends on a problem, but the difficult one, which also tomorrow I will solve a similar problem, it's something that you need to also know for your exam and for future as well. So let's start with method one, the difficult solution. So method number one. So method number one is the Newton, basically, method. We draw the free body diagrams and the acceleration diagram. Let's do that. So if I want to draw the free body diagram for this guy, let me first build my setup so I know what's going on here. So I extend this line. And then I draw a horizontal line here. A little maybe lower. And then I also draw like a vertical line. Oh, we don't need a vertical line. just a tangential line. Okay, so I just draw this line so I know what is what. So what do I have? I have, like always, n, the reaction from the surface, which is normal. We show it by n. Luckily, there is no friction, so we are happy. And then we have, of course, the weight, mg. So, and here we have our mg. All right, so, and the angle, so this is then the vertical. Always try to like make your triangle so you don't make a mistake. So we know this angle is theta, and this angle has to be theta, and this angle has to be 90 minus theta. This is our free body diagram, nothing special about it, and we are all good, right? Now, as I said, we need to draw another diagram here as well. Let me draw it below here, and we call it acceleration diagram. So the same box again. And the box is moving on like an arc, like that. So it's moving on a circular motion. And we know when something is moving on circular motion, we should have two components of acceleration. One is normal and one is tangential acceleration, right? So quickly I say I should have one AN and one AT. This is my AN and this is my AT. All right, so we have a formula for this guy. We know this guy is R theta dot square, and we know this guy is R theta double dot. Remember, for a circular motion, right? And I'm going to write it down here just to remind you. If you recall, like out of laziness, we call theta dot omega and we call theta double dot alpha. But slowly you need to get used to just using this theta dot and theta double dot rather than this omega and alpha. They are the same, but for simplicity, we did that. And we said in a circular motion, you have two components of acceleration. One is AN, or omega squared, and one is AT, which is R theta double dot or R alpha. So this is our then force diagram. So this is the force. And so force diagram. And this is our acceleration diagram. Sort of our job is done now if we get these things right. So if you guys agree with this, let's move on and solve the rest. So all I need to do then is just write this formula that we have, our friend Newton. F is, or sum of the forces is equal to ma. But this is a general formula. I can write it down the way that I want. I can write it down as like sum of the forces in X is equal to max. Sum of the forces in Y is may. Or I can write it down as sum of the forces in T is mat. Sum of the forces in N, man. It's up to me, or maybe any other coordinates that I wish. Like when Newton invented this formula, he didn't tell us that you cannot use it on like a specific direction, any direction that you want. So obviously in this question, we'd better go with the T and N, right? So let's then do the T and N. So let's call this one T direction and this guy normal direction. So this is N and this is T. Let's write them down. And of course, you know how to get the components of this mg. Let me quickly do that. In T and N, so what we get here, it's going to be mg cosine theta, and this one is going to be mg sine theta. Okay, please check if that I haven't done a mistake. This is 90 minus theta, right? Okay, so let me quickly write down. What do I have? Let's start with the t direction. So sum of the forces in t is equal to m at. What do I have in t direction? Well, let's see. We have mg cosine theta. What else? Nothing. Good. It's equal to m at, which is r theta double dot. So far good. We can get rid of this m. We can get rid of this m. And sort of we found theta double dot, which is g over r cosine theta. Okay, so one good thing here. This is where it's getting tricky and I want you to pay attention. We found sort of alpha or theta double dot. We found the angular acceleration, but we need omega, right? Because for us to solve this problem, we need to find a speed. Okay, let me go back to what we started at the beginning. This v, we know this v is equal to r multiplied by theta dot. Do you guys agree on that? Let's come here. Forget this conveyor. This particle that moving on this circle, it has a circular motion, right? And when it has a circular motion, we said it has two acceleration, as you saw, and also it has a velocity. And velocity is always tangent to the path. So if this is our velocity, v is equal to r, but this big R multiplied by theta dot. Okay, this is something that we know from circular motion. And what is theta dot? It's omega. We call it theta dot or omega. So what I'm getting, I need to find out this theta dot. This is my question, okay? This is what I need. I found theta double dot, but I need to find theta dot. So can I integral these things to get theta dot? Yes. But when we integral these things, we need time, right? Because remember, what was the definition of theta double dot? Was the integral of, but the derivative of theta dot with respect to t. Okay, so I can integral these things, but I get to a new problem and I need time. Like I need to know how long does it take to get from A to B. And we'll see in this question, there is no sign of time. So I'm going to write it down here for you, for those of you who think that, okay, let's just do an integral and find theta dot. So I'm just going to write down here. If we try to integrate to get theta dot, we need time, like t. So we don't know how long does it take, and we don't care how long does it take for A to get to B. So this is where we need that formula that I told you it's very important. I also emphasized yesterday. If you recall, we had this formula before, which we said omega d omega is equal to alpha d theta. You remember this formula? We said there is a relation between angular velocity, angular acceleration alpha, and position theta. And this is a key formula that you need to know how to use it. Either you can write it like that, or you can write it in a more, let's say, scary way. Like omega, remember we just said omega is theta dot, alpha is theta double dot. Always I like this one better, like the second one. They are the same, but if somebody look at your notes, they're gonna be scared, right? They say, ooh, this is so advanced. These guys are smart. So let's then get used to using the second formula. So how can I use this formula? I just integral it. So integral of theta dot d theta dot is equal to integral of theta double dot d theta. Always the first, like the left side, it's half of theta dot squared, right? Imagine you are doing integral of x dx. It's just the shape of this x becomes this theta dot. So don't be sort of intimidated by this is just the shape of this, right? So what is then its integral? Half of theta dot squared. Because always we assume we start from speed 0 and we get to some sort of a speed theta dot. Second part, we know theta double dot. I just replace it. It is gr cosine theta. So I started from theta 0, and I'm interested to know what's going on when I'm getting to 90 degrees. But remember, guys, to use the radian here so you don't make mistake. Here doesn't matter, but in general, always try to use radian in this course. So we start from 0. Sorry, and we need to know what's going on when we get to theta 90 degree, pi over 2. So if I do the integral, it's g and r is constant, and cosine theta, so I have the d theta here. Cosine theta, this integral becomes sine theta, and then 0 is 0 and 90 degrees 1. So let's see what we got here. Then can I move myself up here? Okay, so we just found that theta dot squared is 2g over r. We found like the theta, the velocity, basically the angular velocity at this point. And now you can see how we can solve the problem. Let's go back to the original formula that we had, right? R theta dot is equal to R omega. So let's call this one like the star formula. Okay, in a star formula, so R, I replace theta dot with what we just found, 2g over R is equal to R omega. And we were trying to find omega, which we just found it. This omega is just depends on what? It depends on R, the radius, the big radius, and the small radius, nothing else, right? And gravity is a constant. Okay. Now it's time for a question to see if you guys followed all the steps and see if it's clear.
Sorry, Professor, I just have a question regarding the direction of normal and tangential. So I was just wondering, like, regarding the problem that we solved yesterday, I kind of confused that why for that one, the direction of normal was like kind of a horizontal direction, but in here it's in a diagonal form. Mm-hmm. So
okay, no, that's a good question, Mon. So because again, many of you students yesterday weren't in the class, but since this is a good question, let me quickly explain the difference between these two. Mona is asking a very good and important question, and I want you to pay good attention to it. So first, see what's happening here. You have a box which start from A, right, and moving down to B, okay? So this box is moving on a circle, all right? Everybody agrees on that, right? So if I stand on the side and look at these things, what do I see? I see a box like this box is coming down very fast on a circle. So they have a circular motion. Now let's see if I can open question from yesterday where I guess it was somewhere here. Is it here? Okay, maybe I'll just open it here. Okay, it's here. So for those of you who missed yesterday and couldn't watch the videos so far, what we see here, I just want you to think about this question and try to see what you see here. I'll let you guys to read it. So you have like this machine, it's called bobsled. It says apparently 4 people are sitting in it, but we can just see one. And it's spinning, right? It's spinning on these like bowl shape things, like gigantic, maybe you can imagine it's moving. So if you look at the side of these things, what do you see? So Mona, do you see that this guy is moving up and down or left and right? No, right? It's just moving toward you. But if you are like a bird and watch from the top, you will see that the whole thing is moving on a circle.
Yeah.
Like this is the circle, and you will see, like what you will see is on this circle, like this big car is moving on this circle. So what you will see is moving like that, and it's spinning. So the next moment it's here, the next moment is there, and so on, right? So at any of these moments, it has an angular acceleration. Sorry, it has a normal acceleration, which happened for like this moment that we studied here. If we look from the side, the normal acceleration is this in this direction, AN. Okay, I hope it's clear. So there is a difference, guys, then between this question, like this one, these things is spinning on a circle when we look at it from the top, like this is the top view or bird view. I wrote here from top view. This is what a bird can see, right? What we can see is just we see these red things. It's not going up, it's not coming down, it's just staying there. So therefore, our normal acceleration is just because of this motion. Let's move back to the previous one. Was it this one? No? Okay, yeah. But here is a totally different story. It's just let's say 2-dimensional, and nothing is spinning around. If a bird watch it from the top, he cannot see any circle, right? You will see something is just moving from here, like at A, coming down, like the next moment is here, the next moment is there, and then it's here. This is what a bird can see, right? What we will see instead is a circular motion. Is it clear now or no? Like here, if you want to draw the angular acceleration, at any moment, the angular acceleration is toward the center.
Sorry,
I hope.
sorry. I just don't understand why the previous one is spinning and then this one is just sliding down from A to B.
This is because the type of question that we have. This one is like something we leave it at point A and we let it slide down, right? But this question, if this machine doesn't, let's say, move, if we leave it here, of course, it's gonna just slide down. These things are gonna slide down, it's gonna come down. It's not gonna stay there. But if it starts moving with very fast speed, what's gonna happen? It's gonna stay in a certain angle. And it is very similar to this another problem that also you guys see yesterday. Okay. This concept, basically, they are the same. Like this candela, why it stay in a horizontal position when I look from the side? Because of this circular motion, because of this centrifugal force, basically. Okay?
That makes sense. Thank you.
All right. And yeah, try to think about it more. And if it's still not clear, then we can come back to the idea tomorrow during the office hour. So another question. So let's me check from the chat. So should we treat it as a body or as a particle? Like here, particle, we haven't talked about bodies at all. So Felix, are you talking about this question or the previous one? Just for the diagram, this one is we just treat it as a particle. Like that's why I assume that everything is like a dot here. Okay. So if it's okay, guys, I want you to stay for maybe 3 more minutes. So we quickly check method number 2, because it's just going to take a minute. But before I get to method number 2, one more time, let's quickly review what's going on. I will also check to see if there's a question in chat. No, nothing. That's good. So, okay, let's see what happened. One more time. Before solving the problem, we try to understand it, and we saw that, okay, if I leave a particle at A, it gets to a speed V, this red speed V here. And this red speed, because we have a circular motion, is equal to R, this big R, multiplied by theta dot. What is theta dot? Is what we define it here, this how this angle is changing, okay? And we said, intuitively, it makes sense that this red speed is be exactly equal to this belt speed. And belt speed, we know, because we have another circular motion, a small circular motion is R multiplied by omega here. So this is what we are looking after. We want to find out what is this large omega, okay? And all we need, because we have R, we have large R, small r, we need to find theta dot. In order to find theta dot, we use Newton's law. We draw the free body diagram, the forces. We have the normal and we have weight. And then we draw the accelerations. So we have the normal acceleration, AN, and tangential acceleration, R theta double dot. Because we are on a circle, right? The whole thing is on a circle. So Mona, one more thing that you may imagine, what is the center of your circle here is here, right? So everything is more like moving on this big circle, if you can think about it. Not a good circle, but you got the idea, right? So everything is moving on this circle. So that's why we have AN and AT. And then we write the formula, and we were happy until we got to this point, that we found theta double dot. Then we said, okay, that's easy. Let's just integral it, because we want to find out theta dot, right? This is our challenge. And we know theta double dot, if I just do one integral, should be okay. But then I said, oh, wait a minute, I don't have any information regarding time. If the question told me that we want this particle A, it takes 10 seconds to get to point B, then yes, do the integral, be happy. And this is where we need this key formula. And this is a formula that relates three things together without any need for time. It relates angular velocity, angular acceleration, and angle, theta, alpha, and omega. And then we said, let's write it down like in this scary or sexy way, right? It looks a little advanced, but they are basically the same. When you do the integral, always the left side is like that, and then the right side, that's the regular integral. So you find theta dot, you replace it in the formula at the top that we have, and you got omega. Okay? Please note, when we solve this example during the lecture, I made a mistake and I confused this big R with this small r, and we didn't pay attention. So I added this portion after the lecture. Yeah, we just need to be careful. We have like this big R, which is the radius of these sliding things. And then we have this small r, which is the radius of this conveyor. So when I'm writing the formula for acceleration, like down here, this one has to be big R, and this is the big R, because they represent the motion when this particle or this box is sliding down on a circle which has this big radius R. While this small r, we just use it once, and this is where we have to calculate basically, you see the speed of this conveyor, like r omega, right? Because it's the speed of each point for this belt. This is where we use r omega. That's the only time that we use this small r. So then the acceleration is r, and then if we move back and we correct our note, so then here it is r, right? Because I'm replacing at here, and this is r theta double dot. So, and then the rest, this one is r, obviously. And if you go all the way down, we will find our theta dot square to be 2g divided by big R. All right, so this is what we get. And then if we continue, replace everything, so we'll end up with, like at the end, we'll find a speed for omega, which exactly it match with what we found for like using the energy method. All right, sorry for this confusion, but yeah, you noticed it, and I corrected it on the note posted on Canvas. Thank you. So please study it later, and just let me quickly use method number 2. Even I can fit method number 2 here on this small space that I have. So still we need to find these things. So you can see everything is stuck here because I need to know what is this guy, right? What is this V? But if I use energy method, okay, how can I solve it? So energy method, if you recall, we said we have this formula that whatever energy that I have at position 1 plus the amount of work that I do to get from point 1 to 2 is equal to energy at point 2. Okay, for us, let's assume this is our point 1, and let's assume this is our point 2. All right, how much energy do I have? So, and always remember that when you use energy method, you need to set for yourself like a reference line, like this big green line. Always, it doesn't matter, you can put it wherever you want, but you need to specify it, where is your reference for gravity. So let's call it gravity reference. So when I mark your exam, so I need to know where is your reference. So if this is my reference, how much energy do I have at point 1? Everybody should know it is mgh, right? How much work I do to get from A to B? Nothing. It's just a slide down on its own. It's just a slide down because of its weight. No force, nothing is doing any work on it, right? I don't have any external force. If I had friction, well, friction does some work, but negative work, which later, after your midterm, we'll solve problem that involve friction. And what is my energy at point 2? Well, at point 2, I get to the reference, then I don't have any mgh, and all I have is velocity, half of mv squared. So I can get rid of m, and everybody knows what is h. What is h, guys?
Big R.
Exactly, big R. Thank you. See, problem solved. We found v, which is square root of gr, right? And replace it there, you will get the same answer as this one. Done. You see, this solution took like it was super fast and easy and short. So in your exam, if you deal with a question, it depends what the question asks. You are free to use whatever method. However, like this method number 1 is the one that we need it a lot and we use it a lot. So method number 2 is handy. Maybe it can solve our problem here, but the same question, if now the company asks you that we want to know how much force you have at point 2, then the method number 2 doesn't help you. You still need to find theta double dot and then the rest of the story. Okay, I'm going to stop, guys, here. Tomorrow we will have basically extra office hours, which I will answer your question. About your exam, your midterm, the instruction is on Canvas. You join the Zoom on Friday at 8 a.m. regular class, maybe 5 minutes earlier. You need to turn on your webcam. This is the only invigilation that I can do, and I trust on you guys that you're not gonna communicate with each other. It's open book, open notes, open internet, and open everything, any calculators and anything that you want. You can download the questions, like the PDF questions, and print them, then solve your solution on paper, take photo, scan, whatever, and make a PDF and upload. If you don't have a printer, that's fine. You just use a blank piece of paper and write it down on a paper. I will give you extra time for uploading, scanning, printing, whatever. So it's included in the time. And in terms of what materials we'll cover, it's going to be everything that we cover up to now, like at this moment. So it means you will not have any question basically similar to this question, which you need to use energy method and so on. So it's going to be basically the Newton law and the very similar to problem set 1 that you saw, and some of the problems in problem set 2. Like the examples that I solved today, this one and this one are good examples. The problem that I solved yesterday are very important, and also problem that I solve tomorrow. Okay, so these sort of problems that you need to see. So probably you guys need to go to your other class, but I'm gonna stay here if you guys have any question, and I'm gonna record, of course, everything. So if you have to leave.
Sorry, Professor, I just have one more question. I know you said it just right now, but just for clarification. So on exam, we wouldn't expect anything from energy law as well as the momentum and the angular momentum.
No energy, no impulse and momentum. And Felix, yes, tablets is okay, it's even better. So if you have a Surface Pro tablet that you can write digitally on it, absolutely, go for it. Like this is what I'm doing right now, similar to that. At the end, you just save a PDF file, whatever you do, and you upload a PDF file. Yeah, it's going to be a PDF that you upload. And so Mona, if you're still there, yes, it's not going to be any question from energy or impulse and momentum.
Thank you.
Right.
Hi, Professor. This is Kevin Chen speaking.
Yeah, I can hear you.
For the midterm, how many questions do we have? And we have 90 minutes to write it, right? Or
yeah, as I said, 90 minutes. So you might have 3 or 4 questions.
Okay, thank you very much.
Yeah, most likely 3, like each question 30 minutes, but sometimes 3, sometimes 4, sometimes like 2 easier questions rather than a bigger question.
Okay, thank you.
So yeah, 5 minutes before class, you can upload, you can 5 minutes before class, please join the Zoom and you can download basically the PDF file and then basically start writing if you want print or something. And I will be in a Zoom, I'm gonna watch you. And if you guys have any question during exam, I explain. I explain everything on Canvas. Please read that one for the instruction. And what else? Yeah, and at the beginning of the exam, I'll go through the question. I'll briefly explain them in the first few minutes, and then you will start. It's going to be a fun exam. Don't worry, guys.
Sorry, Professor, can I also ask one quick question about this example that is on the screen?
Yes, go ahead.
Thank you. So I was just wondering, I know like we assume that the particle that is like the blue one is like a particle. So we assume it as a particle, but like, can we also draw a free body diagram of this one, or would it be pointless to do that?
So you mean the free body diagram for like this big mass M?
Yes.
Yeah, we can do that. Like, let's say if I want to draw the free body diagram for that big mass M, I'm going to draw it here. So this is the cart. Let's say this is the cart. And what else do we have? So we have this pin here. We'll leave it right there. And then we have these things here. So this is our cart, right? And for us to draw the free body diagram, it means we have separated from ground. And let's see what we have here. So obviously we have the weight of the thing, which is mg. Then what else we have? We have the normal reaction to the tires, which this might be N1 and this might be N2. They are different because we have a pendulum over there. And since this is more like a hinge or more like a hinge or like a pin, sort of, it can revolute and rotate. It has 2 components. One is like this one and one is that one. We call them, let's say if you call this point O, it's going to be OY and OX. And then what else? Well, I either draw OX or OY, or if I'm smart, rather than drawing OX and OY, let's get rid of these. Sometimes my pen doesn't like to. Okay. So, and then I have, instead of this OX and OY, I just draw this T. And basically, this is the same T that we draw it over here for this pin. For this, sorry, M here.
Yes, and then also there is a P acting.
Oh, and also, exactly. Also, we have P acting over here. So this is then the free body diagram for this cart, right? So we have N1, N2 from ground, it's clear. We have the big mass mg coming down. And then we have a hinge or pin, which either we can draw like OX and OY, but this hinge is connected to this like a rod, and this rod is always under tension or compression, which in this case, it is under tension. So it's going to be like T, a low T here, right?
Yes, and can I just know, like, the reason that we approach this question with that pendulum in like the free body diagram of the pendulum instead of this particle, because we don't know what would be the values of N1 and N2.
That's correct. Exactly. Yeah. If you use this one, you see you have a lot of unknown. You don't know N1, N2, and T. But if you use like this small mass M, your only unknown is T, right? But here your unknown is like N1 and N2 as well, which gives you trouble, right? Here you just don't need, your unknown is alpha and T, but here you have the alpha here, you have N1 and N2.